Okay, so section 5.7 is really just an extension of section 5.5, and we'll dig into this right now. So we have found antiderivatives and integrals the following ways in this chapter. Remember when we started 5.1, we just looked at using the idea of the power rule when computing antiderivatives, and then also knowledge of basic derivatives, things like, like the trig functions and things like that, where, if you're doing the antiderivative of cosine, you say, oh, well, the cosine is the derivative of sine, so you can think about it that way. And then most recently, we've seen that we have these more sophisticated methods involving u substitution for doing antiderivatives of composite functions, where you do the u sub for the inner part of a composite function. Now we add a few new strategies to the list, and these are the topics that we're going to cover as we wrap up the class. In 5.7, we look at u substitution for the entire denominator as a possibility, and we also look at doing a u substitution for your terms involving natural log, again, as a possibility. And then in 5.8, after we take the test, we're going to talk about a u substitution for inverse trig derivatives, just because I don't want to confuse you too much right now. So always kind of try to do antiderivatives using these original strategies that we've learned, and then if those don't pan out, then consider some of these others. And we're going to be working with the integral of 1 over x throughout this section, and we've already seen before that the antiderivative of 1 over x is the natural log of the absolute value of x plus c. Remember, the derivative of natural log of x was 1 over x, so it makes sense that this is the case. And this absolute value is here because you can only do the natural log of a non-negative quantity, but in this context, you're not necessarily restricted to non-negatives. And so that natural log of the absolute value of x is necessary here. And in terms of u substitutions, this is what we're going to be going for in a lot of the examples in 5.7. du over u, or 1 over u du, is equal to the natural log of the absolute value of u plus c. Okay, so let's take a look at a few of these examples, and I'll show you what I'm talking about. So example 1. When I look at this, I can't think of the power rule. I can't think of applying the power rule. I can't think of this as being the derivative of a function that I'm familiar with. Maybe I don't recognize this as a composite function. And so here I'm going to go back to the u sub, or this new strategy of a u sub for the entire denominator, and see if that's going to help. So I'm going to start this, and I'm going to write u is equal to 4 minus 3x. And if u is equal to 4 minus 3x, going back to the last section, du would be equal to negative 3 times dx. Now, we don't have negative 3 times dx, but I can make that happen. And if I put a negative 3 in the integrand, then I'm going to offset it with a negative 1/3 in the front. So my integral becomes negative 1/3 antiderivative of du divided by u. And that's actually pretty easy because the antiderivative of du divided by u is natural log of the absolute value of u. And we'll say plus c. So this is just negative 1/3 natural log of the absolute value of what our u is equal to, 4 minus 3x, and then plus c. And just as a reminder, once again, whenever you get these antiderivatives, you can take the derivative, differentiate, and see if the derivative gets you back to the original integrand. Okay, number 2. So when you take a look at this one, we can see right away that we can apply the power rule or knowledge of derivatives. And maybe you're thinking that this is a composite function down here with this x cubed, and that's definitely one way to go, but you'll notice if you let your u equal x cubed, then your du is going to be something involving x squared, and we don't have x squared in this problem. And so we could typically modify integrands with constants and things like that we've been doing on the last couple of sections, but we can't modify integrands with other functions of x. So what I would do here is I would begin this by actually applying a property of logs. And this is a little thing to look for in some of these examples, and we're seeing it here. When you're doing the log of x to the third, that's equivalent to, this is completely equivalent to saying this is the 3 times the ln of x. So if you basically bring that 3 in front, you have 3x times the ln of x, and this is before we even get started. And so I guess the way that I approach this question, I'm kind of looking at it like this, where I have 1/3, so you pull that out in front, I have 1/3 times the antiderivative of dx over x times the ln of x. And if you try to use a u substitution on the entire denominator, you're never going to have the du appear in this integrand. And so this is where I'm going to go to my second bullet from above, doing a u sub for a term involving the natural log of x. I'm quite literally going to let u equal ln of x in this case. And watch what happens. So this becomes 1/3. Oh, I guess I should say du is going to equal 1 over x dx. But when I have that, isn't 1 over x dx the same thing as dx over x? And that is what this is right here. So that is my du. So I have my du in the numerator all over my u in that denominator. And so sometimes letting u equal natural log of x allows you to get the du that you need for getting du into that integrand. And here we could finish this out by just saying this is 1/3 natural log absolute value of u plus c, and we'll just substitute in what our u is. And I know this is kind of strange. We end up with 1/3 natural log of the absolute value of the natural log of x plus c. But this is entirely possible. The natural log of x can take on values that are positive or negative, and so therefore you still need the absolute value there, and you could be doing the natural log of the natural log of x like this. So this is our answer for number 2. Okay, number 3. We're doing the integral of tangent of theta d theta. And you might be thinking, well, didn't we do this before? Well, we actually didn't. We only know the antiderivatives, or the indefinite integrals of sine and cosine. We don't know them for tangent and the other trig functions just yet. But we can apply the ideas that we've been working on to come up with this. Because tangent is the same thing as sine of theta over cosine of theta. And you could look at this and say, okay, well, maybe I'll do a u sub for that denominator. So that's one of the new ideas in this section. And this isn't something that you always want to do, but in some cases, a u sub for the entire denominator will allow you to end up with a du that is also involved in that integrand. And in this case, we see that because if u is cosine, du is negative sine of theta d theta. And I don't have negative sine of theta d theta, but I can make that happen. Negative inside, negative outside, so this becomes negative antiderivative of du over u. The antiderivative of du over u is natural log of the absolute value of u plus c, and then you would back substitute to get negative natural log of the absolute value of cosine of theta plus c. So this right here is the antiderivative of tangent of theta. So the antiderivative of tangent is a little bit more complicated than the antiderivatives of sine and cosine. But it can be computed based upon integration by substitution and using the new techniques that we're seeing in this section. So I'm going to stop this video now, and I'm going to actually derive the antiderivatives for the other trig functions, and then we'll apply those in the next video.